When your program runs, the CPU is constantly making decisions. Every time your code reaches an if statement, a loop, a function return, the processor must decide what instruction comes next. But here's the problem. Modern CPUs are incredibly fast. They execute billions of instructions per second, and they don't like to wait. If the processor had to pause every time it encountered a branch, every conditional jump, performance would collapse. So instead of waiting to know what will happen, the CPU guesses. That guessing mechanism is called branch prediction, and it is one of the most important performance features in modern software execution. Today, we're going to explain what branch prediction is, why it exists, how it works at a high level, how it connects to instruction dispatch, and why it directly affects the speed of your code. Let's start with the basic problem. At the lowest level, execution follows a simple cycle. Fetch the next instruction, decode it, execute it, update the instruction pointer. In straight-line code, this is easy. The instruction pointer simply moves to the next memory address. But software is not straight lines. Software branches. An if statement creates two possible execution paths. A loop creates a conditional jump back to the top. A switch statement creates multiple possible targets. At the machine level, these become branch instructions, instructions that may change the instruction pointer to a different address. And here's the issue. When the CPU encounters a branch instruction, it often doesn't immediately know which path will be taken. For example, imagine a simple condition. If a value is greater than 0, jump to one address. Otherwise, continue to another. The CPU must evaluate the condition. But evaluating conditions takes time, and modern processors use pipelines. They overlap instruction execution to increase performance. A pipeline works a bit like an assembly line. Multiple instructions are in different stages of execution at the same time. But pipelines depend on knowing what instructions come next. If the CPU reaches a branch and doesn't know which direction to go, the pipeline stalls. A stalled pipeline means wasted cycles, and wasted cycles mean slower programs. Branch prediction exists to prevent that stall. Instead of waiting for the condition to be fully resolved, the CPU predicts which branch will be taken. It speculatively continues fetching and executing instructions along the predicted path. If the prediction turns out to be correct, execution continues smoothly. The pipeline remains full. Performance stays high. If the prediction is wrong, the CPU must discard the speculative work. It flushes the incorrect instructions from the pipeline and resumes execution from the correct path. That flush is expensive, so branch prediction is fundamentally about this trade-off. Guess early to keep the pipeline busy, pay a penalty if the guess is wrong. Now let's go a bit deeper. How does the CPU make these predictions? At a very basic level, early processors used simple rules. For example, they might assume that backward branches, like those in loops, are likely to be taken. That makes sense. Loops usually execute multiple times, but modern CPUs use far more sophisticated techniques. They maintain hardware structures that track past branch behavior. If a branch instruction was taken the last 10 times, the CPU predicts it will likely be taken again. This is called dynamic branch prediction. The processor essentially learns patterns in your program's control flow. Some predictors use small bits of memory per branch instruction. Others use global history of recent branches. High-end processors combine multiple prediction strategies and choose the most accurate one dynamically. All of this happens in hardware, and it happens extremely fast. Now let's connect this back to instruction dispatch. In the previous video, we explained that dispatch determines the next instruction to execute based on the instruction pointer. Branch prediction influences dispatch by deciding what the next instruction should be before the branch result is known. In other words, dispatch doesn't wait. It moves forward based on a prediction. If correct, dispatch flows smoothly. If incorrect, dispatch is redirected and the pipeline is reset. This is why unpredictable branches can hurt performance. Consider a branch that depends on random input, something that is equally likely to be true or false. The CPU cannot form a stable pattern. It predicts one direction. Half the time, it's wrong. The pipeline is flushed frequently. Performance drops. On the other hand, consider a branch inside a loop that runs 1,000 times. The condition I is less than 1000 will be true almost every time until the final iteration. The CPU quickly learns that this branch is usually taken. Prediction becomes highly accurate. Performance improves. This is one reason why tight, predictable loops are fast. Now let's discuss the cost of misprediction. When a branch is mispredicted, the CPU must discard all the instructions it executed speculatively. That can mean flushing several pipeline stages. On modern processors, a misprediction can cost many cycles, sometimes 10, 15, or even more. In high-performance code, those penalties add up. This is why low-level performance engineering sometimes focuses on reducing unpredictable branches. For example, some algorithms are rewritten to reduce conditional jumps or replace them with arithmetic operations. Not because conditionals are bad in theory, but because unpredictable control flow is expensive in practice. Now let's introduce another important idea: speculative execution. Branch prediction and speculative execution go hand in hand. When the CPU predicts a branch direction, it doesn't just fetch the next instruction. It may execute multiple instructions ahead speculatively. It assumes the prediction is correct and continues processing. If the assumption holds, those results are kept. If not, they are discarded. This speculative behavior increases performance, but it also introduced important security discussions in recent years. Certain vulnerabilities exploited speculative execution side effects, showing that even discarded work can leave traces in caches. That's a deeper topic, but it shows how fundamental branch prediction is to modern processor design. Now let's zoom out and connect branch prediction to software design. Most developers don't think about branch prediction when writing code. And in most cases, you don't need to. Modern CPUs are very good at predicting common patterns. But if you're writing performance-sensitive systems, game engines, high-frequency trading systems, database engines, embedded firmware, control flow matters. Highly unpredictable branches can become bottlenecks. Data-dependent branches on random input can degrade throughput. Large switch statements with scattered targets can affect instruction cache behavior. So understanding branch prediction gives you a deeper mental model of why certain patterns are faster than others. Now let's clarify something important. Branch prediction does not change the logical correctness of your program. It only affects performance. Even if the CPU predicts incorrectly, it will eventually execute the correct instructions. Prediction errors are corrected before results are committed. From the perspective of your program's behavior, everything remains deterministic. From the perspective of timing, however, it can vary significantly. Now let's address a few common misconceptions. First misconception: branch prediction is a software feature. It is not. It is implemented in hardware inside the CPU. Second misconception: branch prediction guarantees performance. It does not. It improves performance on predictable control flow, but unpredictable patterns still incur penalties. Third misconception: branches are always bad. They are not. Predictable branches are cheap. Unpredictable ones are expensive. Fourth misconception: modern CPUs don't rely heavily on prediction. They rely on it more than ever. Without branch prediction, deep pipelines would be impractical. Now, let's bring everything together. Software execution is built on instruction dispatch. Instruction dispatch is influenced by control flow. Control flow is shaped by branch instructions. Branch prediction exists to make dispatch efficient in the presence of branches. Without branch prediction, modern processor performance would collapse. With it, CPUs can execute complex software at extraordinary speeds. At its core, branch prediction is about one thing: keeping the pipeline full, keeping execution moving forward, avoiding idle cycles. So the next time you write an if statement or a loop, remember that under the surface, the CPU is not just executing your logic, it is predicting your logic. It is making educated guesses about the future of your program's control flow. And most of the time, it guesses correctly. That silent guessing is one of the reasons modern software feels fast, and it's one of the hidden mechanisms that make large systems possible. If you want to continue deeper into the execution model, the next logical step is exploring CPU pipelines and out-of-order execution. how instructions are rearranged internally for even greater performance. But for now, you can reduce branch prediction to a simple principle. The CPU predicts the next control flow path to avoid waiting, and that prediction keeps software running at speed.